Hey folks, my name is Mateusz. I'm an engineer at the Oasis protocol. So this is the first slightly more technical workshop on how we can use Oasis Sapphire to build confidential dApps. So I will focus on how to make the confidential voting dApp on Sapphire, and along the way I will also present some more fancy features we developed during the last year. The random number generator, the key pairs, and so on. Right, so first the essentials. In the morning, Jarne already showed you this illustration. So the figure shows the architecture of our platform. On the top side, there's this consensus layer. This is a thin, pretty simple layer, which is there for the governance, for funding the accounts, for registering and governing the paratimes. And the paratimes are separate chains which are shown below here. So first, the Emerald paratime is a paratime we introduced a few years ago. This is an EVM compatible paratime, but it does not offer any confidentiality. Then we introduced Cypher. This is the first paratime that actually supported confidentiality, but it uses our own dialect, Oasis dialect of the WASM. And finally, there's this Sapphire. So the Sapphire is the first confidential EVM, let's say 99% EVM compatible paratime currently. So we'll focus on the paratime, on the Sapphire paratime today, because this is also the current bleeding edge technology that Oasis offers. Right, so first let's see how a simple confidential transaction works in Oasis. So here we use the end-to-end encryption. The client and the Oasis platform will use the symmetric key. The client derives its own key pair. And on the paratime side, the paratime has this ephemeral key pair available, which changes every epoch. That's roughly every hour. And the first thing is that when the client generates the key pair, it requests this ephemeral public part of the key, and it encrypts, it derives then the symmetric key and decrypts the transaction with it and sends it, right? So this goes through the Web3 gateway, of course. I'm not showing those here. This is just the Oasis node, the compute nodes shown here. Now, what happens on the paratime side? Well, the first thing is that it needs to decrypt the transaction. To do this, it requests the ephemeral paratime, but this time the private key as well. And it combines the private part of the ephemeral key with the public key of the client, which he sent along, right? So now he decrypted the transaction, but still there is another key pair we use. So apart from the encrypting the transactions and the communications between the client and our platform, we also use internally another key pair which encrypts the contract state. So he gets this contract state key pair from the key manager each time. So it cannot, like some networks also had issues in the past that each of the nodes contain the master key, and if the trusted execution environment broke, for example, then one could exploit this master key. Well, in our case, the compute node must request this key pair of the contract state key pair from the key manager each time. So once he got that, he can decrypt the contract state and execute the EVM transaction. And also any side effects that happens afterwards, the contract state is changed and rolled back. Okay. Now, Sapphire supports both the traditional non-encrypted native EVM calls and transactions and the Oasis confidential ones, the encrypted ones. Now, I'd like to stress out here the another property. So regarding the calls, if you recall, in EVM, the contract calls can change the from field, and this basically sets the message sender field inside the contract to arbitrary value. So, for example, the ERC20 has this get balance call where you deliberately change the message sender if you want to get the balance of some other account. Here we deliberately decided that the message sender will always match the signer of who who signed the contract call. If the call is not signed, then the message sender will always be zeroed out, right? So this is, if you remember back, I mentioned that we were 99% compatible with the Ethereum EVM. Well, this is the 1% where this comes from, right? So you cannot, if you have a DApp which uses this property, which exposes this setting custom values to this message sender, this won't work on Sapphire. Okay, and the last property, just keep in mind that events are public on Sapphire as well. So if you put any sensitive information inside the event message, those will be visible by anyone. So you need to do this encryption, on top of that if you want to get encrypted emitted events. Okay, so now if you imagine if you want to verify a deployed contract, so Sapphire stores the contract bytecode unencrypted. This was already this was also a decision we made. So all the contract code is public in that sense, but there are two kinds of contracts. One are the immutable, and the other ones are mutable. So if you're using the immutable contract, those are the ones which have the constructor with some parameters. The contract call, the contract trade call, will also include those parameters along, right? So if you do the encrypted contract create transaction, then those constructor parameters won't be visible, and external services like the Sourceify won't be able to verify it. So usually how DApp developers should treat this issue is that let the contract deploy transaction be public, and every other transaction afterwards can be encrypted as you want. So this is the way how you can verify the contract. Okay, so what about the contract state? If you look at the private and public properties on Ethereum, so if you look at the fields, not the methods, but the members, the fields of the contract, one can always dump the contract state and extract the values of each contract variable, right? Well, here this is not the case, because the contract state, as I mentioned earlier, is really encrypted. So if you have the private variable, in this case we'll call ballots, _ballots, this variable will remain private, and there is absolutely no way, unless you break the encryption mechanism, to extract the value of the ballots, while the proposals in this case is defined as public, and on the chain level the proposals will also be encrypted, but we will offer automatically the getter and setter methods, and the value will be decrypted and returned to you. So if you declare it as a public field. Now let's look at our toolkit. So you will mostly use 3 npm packages. The first one is the Sapphire Paradigm. This is mostly focused at the front-end apps, so MetaMask, Truffle, and it injects the code necessary, for example, into MetaMask, the necessary code to encrypt the transaction, fetch the ephemeral key from the paradigm, and do all the confidentiality and encryption and so on. The Sapphire Hardhat is a wrapper that takes the config file of your Hardhat project and wraps it so that you communicate this ethers object is now using the encryption and automatic signing. And usually you, in the code, we'll see later, that you make 2 instances. One is for the signed transactions, one is for the unsigned contract calls, for example, because each time you want to communicate, each time you want to send the signed transaction or signed call, the MetaMask pop-up will appear and show you something. So in this case, you will want to use the unsigned wrapper for this. Now the last package are the Solidity precompiles, Solidity wrappers for our precompiles. So in the last year, Sapphire, we added a bunch of very useful, fancy precompiles into our platform. One is for generating the pseudo-random numbers, the RNG. One is for deriving the symmetric key from the private-public key pair. You can sense now that this can be used to do the on-chain thing, something. And then we added this the Oasis 2 encryption and decryption primitives, which is used by the communication between the client and paratime as well. And we also added the ED25519 and SACP key pair generation on-chain, so we can generate a key pair completely on-chain, and of course that's because we support the random number generator. And finally, you can assign and verify a message on-chain. So why am I talking about this? Well, what we support now is that we can actually wrap the contract, sign it on-chain, and the user can simply submit it, and you get, for example, the gasless voting or the EEP 4337 Vitalik talked about yesterday for free. Okay, another feature, another useful tool, put it this way, is so because our tooling is compatible with the original Ethereum EVM, you're free to use, the hardhat node command to run your chain locally, non-confidential chain locally, and just test out your smart contract. But if you're using any precompiles I mentioned earlier, then you will need the fully flavored Sapphire paratime running locally on your machine, and we offer Docker images for this. And basically, it contains everything from the Oasis core node to the 3 compute instances, the Web3 gateway you'll be using, and some helpers to fund basic wallets, so you can actually run your app locally. Okay, so now let's go to our app. So the voting, probably the EVoting issue or the problem is a very old problem, I'd say. And if you're organizing a ballot, then let's see at some stuff that you need to take care about, so that everything will be right. So first, only the eligible voters can vote and should be able to vote, whereas the non-eligible ones must not vote at all, right? So this is the first thing to keep in mind. The second thing is anonymity. So if a voter submits his vote, there should be no way afterwards to determine which voter submitted which vote. So you should not be able to link the vote with the voter, right? Still, it should be transparent. So the votes in the ballot box should be trusted as the ground truth that, yeah, these are the votes that the voter submitted, and we should, count it and suppose that they are fair. And then the last point is more of a, social politics issue, which cannot be probably solved by the technology. So anyone must be given a chance to vote and not being forced to vote, and they should be able to vote by their own conscience, right? So this is something we are not actually tackling on our platform. Right, so, but still, I mean, no voting is ideal in real life, so it's more of a question whether we can make a good enough voting app on our blockchain. And why is that? Well, because blockchain is, if you're using a public blockchain, this seems like a perfect natural platform for doing such important thing as elections, right? So the Sapphire, I mean, we already knew this e-voting mechanisms before, but the Sapphire is really, simplifies the way how the elections can be made, and this is because it's using this trusted execution environment. Okay, so now look at some Solidity structs we brought. So this is not a part of the protocol, and the dApp we developed should not be, Oasis should not be eligible if anyone, uses this and something goes wrong. But just let's look at how easy and straightforward it is to write a ballot on our platform. So the proposal, this is basically the elections, right? Is it active? Then we will store the IPFS hash. So the reason why we decided to use IPFS is because you usually, suppose you have local elections at municipality, you want to vote whether to use one or second or third railway route, and you want to also show a map where the railway is planned, to be laid, and you need to store those images, those figures somewhere, right? And they should not be hacked, right? So what you do, well, basically you just store them on the IPFS and you reference them from the blockchain. So this IPFS hash field here stores exactly this. The number of choices is just simply how many choices the voter has in the proposal, because this is something that will be stored on-chain. The published votes Boolean variable is here mostly to be compatible with, does anyone know Snapshot platform for voting on project proposals? So Snapshot has this feature of showing which account voted for which option. And here we added it here so we can also support it. But on real, elections for the mayor or for presidential elections, this Boolean should be, just ignored. And then once the proposal is closed, there's this top choice, which means which option won. Okay, so these proposals will be a public field in our contract, right? So here, usually if this were some presidential elections, you would just have, a single DAO instance with just a single proposal. But here we support like multiple proposals, so anyone can try it out and play with it. So this is the mapping, it stores the proposals. Okay, now the confidential part. How do we store the voters' ballots? So each voter constructs this choice. It is just a simple, which choice did I make, which option did I check. This exists here is just a helper, because when you're fetching, if the voter voted already or something like that, the solidity will automatically, just a syntax sugar, will automatically generate a choice for you, but this exists will have false value. So actually stored voted values will have this set to true. Right, and once the voter votes, this vote counts is increased for the specific, choice. So this is the aggregated value, and eventually, once the ballot closes, the maximum of the fields inside this vote counts field is the one who won, essentially. And this ballots field contains the voters' ballots, and it will be private. So it will be accessible only from inside the smart contract. If you dumped the contract state, you'll just get some random encrypted blob, right? Okay, now another structure I'd like to present is the access control list. So I mentioned the eligible voters. So here there are multiple roles. It's not only the voters, it's also the poll managers, like who can manage the poll, who can create it, who can close the poll. And we just define the interface, and DAO can then use any concrete access control list implementation which implements this interface. So basically can create poll, can manage poll, can vote on poll. So if you were to have, I don't know, just n number of eligible voters, there will be like n entries inside this ACL contract, and the can vote on poll will be set only for the eligible voters. So this is the address of the DAO, because ACL can also cover multiple DAO instances. That's the elections, what we're checking, and this is the address of the voter, potential voter, that we wanted to know if he can vote. Okay, Now, the latest addition to our platform, GasFree Voting. So the idea is the following. You want to have elections on-chain, but the voters, of course, they should not be required to have tokens native tokens for your platform that has the elections. So how do we implement the gas-free voting? Well, the gas station network. So we forked the OpenGSN project to add the encryption. So the idea is that you don't necessarily need to trust the relay server, because you encrypt the transaction using some key. And this key is stored on-chain. This is not the ephemeral key I've been talking about. This is also not the contract state key I've been talking about. This is relay hub specific key stored inside the relay hub contract. And the idea is, why do you encrypt it? Well, because you don't want your relay server to sniff your vote, right? So you send the transaction to your relay server. It relays it. It asks the paymaster if if the voter is allowed to vote, and so on. It simulates, gets the gas cost, and so on. It decrypts it inside the contract, and then the call can be forwarded. Right. So this is just standard gas station network implementation. It's in the early beta phase, let's say, but it works. Yeah. It's slightly complicated though, so you need to extend, as any other GSN solution, this ERC-2771 recipient contract, and you need to set the trusted forwarder and so on. But from the developer's point of view, the only thing you need to use is, instead of importing the @OpenGSN packages, you use the @Oasis Protocol /OpenGSN packages. Yeah, and you can check out this for details, for documentation and examples. Right. Now, the Oasis specific feature is the OnChain Signer. So I already mentioned before that the contract status is fully encrypted. So why not use this super feature to store the confidential keys and to create a transaction and sign it? So this is exactly what we did in the past few weeks. So basically, the client sends the vote on-chain. The vote is encrypted using the ephemeral state, the paratime ephemeral key, and then on-chain the transaction call is decrypted. It is wrapped with another transaction signed by someone that has gas, and those keys are also stored inside this gas layer gasless voting, for example, contract. And then this transaction, wrapped transaction, is returned back to the client, and the client then just simply broadcasts the transaction, and if everything goes well, the vote is then accepted. Yeah, okay. So compared to this diagram, you have this relayer intermediary here. So these are a bunch of Web 2 services which you then connect to, and that they relay transaction for you. Here you communicate with the blockchain directly. I mean, there is the Web 3 service in between, of course, but if you don't trust it, you can always run your own node, client node, and run your own Web 3 gateway, and this will work fine. Okay. Right. So now time for the demo. How much time do I have? So here is the source code. You can check it out. But perhaps I just go through some more high-level details. So the DAO contract works like this. So the internal cast vote, for example, if we focus on this one, this is the core logic of when someone submits the vote, what happens inside the contract. So we check the ACL, the access control list object, if the voter is eligible to vote. Then we get the proposal, we get the ballots, and then we do some arithmetic magic below here. So the reason why we do this is to mitigate the access patterns inside the contract, right? So the contract state is still encrypted, of course, but if someone is running, an adversary is running his node, and he wants to examine the access patterns to the memory. This is, I mean, the memory is encrypted, but the access patterns are not encrypted, and he can, observe it, which memory cells are being accessed inside the trusted execution environment as well. Then he would, assume that if there is a bias towards one, field inside that memory cell, one cell inside the memory, then that cell probably contains the amount of votes someone got, right? So the idea here is basically you go through all the candidates, you change all the options, and then you just, subtract, add one, and then subtract that one at the end, so you get, the correct number eventually. So this is, one way of solving this issue. And then we also then mark here that, the voter already voted, because we also support, that you can change your vote during the time the poll is still open and so on. But this is just, another feature which is not common to traditional, elections. Right. So why is this called internal cast vote? Well, you can see that this function is called either from here, the cast vote, and this function is declared as external. This is when the user has enough gas, he can call the DAO directly and pay for gas and submit the vote, right? And it just redirects it to this internal cast vote, and the first parameter here, so this is the voter address, is assigned the message sender, right? And now you would say, what happens if I, submit the transaction? Well, the transactions are always signed, so, the calls, contract calls can be unsigned. In this case, the message sender will be zeroed out, but since you will send a transaction to the cast vote, then the message sender will always, be defined. And if it's not eligible, the ACL here will fail. Right, so this is direct voting. What about if we use the proxy? So if you use the gasless voting. In this case, I think is it proxy vote? Proxy vote inside the DAO. Sorry for this. Yeah, here it is. So this is a proxy vote, and this is called by our external, the proxy gasless voting contract. And it just checks whether the proxy voter object is really the one who's calling this function, and it then forwards it. And the voter is not the message sender, of course, because the message sender will now be the proxy voter contract. It forwards the one voter that is passed already to this proxy vote. And this proxy vote, where is it called from? It's called from the gasless voting proxy. Let's see, proxy vote. Sorry. Proxy vote. Oh, sorry. Yeah. It's inside the request. So we have generic request, generic proxy function. And the client encodes which transaction, which function should the proxy call. So it's not directly, but it's here when the call is being made. So basically, it decodes the transaction, and then based on the address the transaction contained, it performs the call. Yeah. Okay, so this is the backend part. What happens on the front end side? Let's see at the cast vote. Right, so the ordinary, confidential voting with paying the fee for the fee is very straightforward. So basically, you first switch the network to the Sapphire paradigm either testnet or the mainnet, depends. And then you just, call the cast vote. And you call it on this DAO instance, which is in fact the wrapped confidential interface to the DAO contract on Sapphire. Because we also use, and when you do this, the MetaMask pop-up will, the MetaMask will pop up and want you to, sign this message, sign the transaction, and then it will submit it. But if you just want to use the unsigned transactions, which are, really all called from the background, and you won't notice it, you usually want to have this unwrapped DAO instance, which you can also get. Right. So if you look at the gasless voting, this is this block here. It's again, it's a bunch of statements here required to get the gasless proxy and so on. But essentially, what you do is that you sign it locally, and then you, then you call the make vote transaction, and this is the on-chain transaction I've been talking to you about, that it wraps your vote and signs it with some account that has enough gas, and it returns it to you, and you get it here in this TX variable. And then basically you can send it over an unwrapped provider, unencrypted, because the content of the transaction is already encrypted for you by the proxy. And yeah, this is it. So let's go to the demo. I invite you to scan the QR code, or just head over to the playground.oasis.io/demo voting. And if everything goes well, you should be able to see the poll and submit your vote. Maybe if I should put this QR somewhere. Yeah, it's, or you can just type in manual like playground.oasis.io/demo voting. MetaMask. Okay, let's click on it. Okay. So it looks like this. I mean, we added a bit of, we customized it a bit for this EthCC event. So I already made 2 polls here. And so currently anyone can create a new poll which has gas. So it's not, the ACL allows anyone to make a new poll, but you need to pay for gas. And for the voting, anyone can vote, and you don't need to pay any gas. It's a gasless transaction, demonstrating the latest Sapphire functionality. We generated 10 funding accounts on-chain, and they're funded, I think, with one token. So that's enough to cover a bunch of votes. And the account linked, the funding account you will get is randomly chosen. So it's just a random round-robin way of getting the correct account. And now you would ask, why did we decide to use, 10 accounts? Why just not use a single paying account? Well, the Ethereum transactions, the EVM works in a way that you can only have, one transaction per nonce. So this means that if 10 voters wanted to vote at the same time, you would basically get a wrong nonce because only one voter will go through, and the rest of the voters will need to increase nonce by 1, wait for the block to get mined, and then resubmit the vote. And here basically the chance of having 2 voters using the same nonce and the same signer account is, well, reduced, right? So that's the idea. Maybe the logic, for waiting if the vote fails, should be extended for that it waits like for 2, 3, 5, blocks, if someone else happens to get the same signer account and so on. But yeah, I mean, the core idea is here. Okay, so let me try it out. Suppose, so hopefully not all the network community will now, try out my demo and nothing will work and only all the signer accounts will be duplicated. Okay, let's try French dessert. So what I did was, if you noticed, I picked one account that has 0 tokens, right? And okay, this is perfect, scenario for a cyber attack. You just generate like 100 random accounts and submit 100 votes. But well, okay, without whitelisting because we haven't enabled whitelisting, right? Okay, what do I like? I like vanilla crème brûlée, maybe. Okay. And now the MetaMask will still require from me that I sign my vote, right? Okay. But it will not require from me paying for gas. So yeah. And now the transaction is, okay, maybe I should show the developer log. Yeah. So the transaction, okay, was generated and was submitted. This is the transaction I got. So if I go to the Sapphire Testnet Explorer. Oh, sorry, wrong one. Testnet Explorer Sapphire, this one. And if I paste the transaction ID here, yeah, here it is. So the transaction seems to went through. Let's see if it did. Yeah, it also did. Okay. Now the interesting part is this. So I voted for the second option. This is choice ID 1. And if we look at the body, the transaction body, it should be something like, yeah. So you have this ciphertext nonce field, which has some value. So this is the account nonce used for the for signing the transaction, and is encrypted, as you can see. And then there's this data field, which actually contains our vote and some other proposal ID and so on, is also fully encrypted. And this ciphertext here can only be decrypted on chain, and there is absolutely no way, as I mentioned earlier, without breaking the encryption, that you see what someone voted by this. Okay, so this concludes my demo. And if there are any questions, thank you.